Okay, welcome to example 9. We have a small hydroelectric plant in the mountains that brings water from a reservoir, which is shown over here at 1 and 2 area. And in these enclosed tubes all the way down here, at the very bottom at number 3, we have the turbine. Now, it tells us that the diameter of the intake tube, that would be number 2 here, is 100 centimeters, and the diameter on the nozzle at the end here, number 3, that goes into the turbine is 50 centimeters. And so what we're trying to find is the water speed that is going into the turbine. So really, what is the velocity at number 3? So let's start off by labeling all the different things that we have that it's given. We're trying to find velocity 3. That's what question A is asking for. And we're given a few things. We can assume that right at position 1 here is air, and we'll need to also assume here at position 3 there's air here. But in position 2, that's obviously in the middle of the fluid, so this is water. Now, this is a question that's going to involve two things. We have Bernoulli's equation, and we also have the continuity equation. So we're going to assume that this water is an ideal fluid and that it obeys Bernoulli's equation. And we'll have to consider that there's a nice streamlined flow that flows from 1 to 2 to 3. And we'll assume that pressure 1 is the atmospheric pressure, and pressure 3 is also the atmospheric pressure. But pressure 2 we don't know, and in fact that's what we're going to be finding is what is the inlet pressure, which is pressure 2. So B part is asking for the pressure at 2. Okay, now there's a couple things that we need to do in solving this problem. When we look at 1, this is a very large reservoir, and so we're going to need to make an assumption that the area, the cross-sectional area at position 1 is quite large. So we'll assume that area 1 is much, much larger than area 3, or even area 2. And since that's true, then we can say that velocity 1 is much, much smaller than velocity 3. And this is true because the area times the velocity equals the area times the velocity. The rate of flow of the volume that is flowing at 1 is the same as the volume flow at 3. But because area is quite large here, this just crawls down, and we can assume basically that velocity 1 is, since it's so small compared to number 3, we're going to make the assumption that that is basically 0 meters per second. Okay? And also we've assumed that pressure 1 and pressure 3 are the same. So to solve A, we're looking for the velocity of 3. And this involves Bernoulli's equation. P at 1, that's pressure at 1, plus rho g y1 plus 1/2 rho v1 squared equals pressure at 3, which is down here at the turbine, plus rho g y at 3 plus 1/2 rho v3 squared. So, now let's take a look at this a little bit more carefully. We have pressure at 1 and pressure at 3, and they're the same. So pressure 1 and pressure 3 will cancel out, since pressure 1 and pressure 3 are basically the atmospheric pressure. Well, probably it's actually a little less than the atmospheric pressure because they're really up in the mountains. But regardless, both of these pressures will be the same. We also have that velocity at 1 is approximately 0. So that means this term right here is going to go to 0. Then we make a simplification here in that we have two vertical heights, y1, which would be the distance from here to here, and y3 is this distance. Now, I would assume that the lowest position, y3, is 0. So that means that this term will go to 0 because y3 equals 0. So essentially what we get is that the rho g y1 term is left on the left side, and then we have the 1/2 rho v3 squared term on the right side, and everything else has canceled or gone out to 0. The densities cancel out, and so that the velocity at 3 is really just the square root of 2 times acceleration due to gravity times that height that the water started from. So let's plug in our values. So we have 2 times 9.8 meters per second squared times a total height of 250 meters. I guess I didn't write that down here, but y1 is 250 meters. And so you can go ahead and plug that into your calculator, and you'll get exactly 70 meters per second. Okay, now let's look at part B. What we're trying to find is the pressure down at level 2. And the common mistake here that people will make is this. They'll go pressure at 2 equals the pressure at 1 plus rho g h, which is what we learned in the last few sections in this chapter. But there is an issue with this. You've forgotten that the water is moving along from 1 to 2, and when it gets down to 2, it's actually flowing. When we use this, we were assuming the fluid was static, not moving. But this water is actually, when it gets down to 2, it's actually moving along through this pipe. So really, this would be an incorrect approach. So I'm just going to cross that out. And let's really look at it through Bernoulli's equation. So what we're trying to find is the intake pressure at 2. So let's go from point 1 to 2. Now you could also go from 2 to 3, but I'm just going to look at 1 to 2. So the pressure at 1 plus rho g y1 plus 1/2 rho v1 squared equals the pressure at 2 plus rho g y2 plus 1/2 rho v2 squared. Okay, now pressure at 1 is the atmospheric pressure right here. Y1 is now going to, I would assume that to make this problem a little bit easier, let's make Y2 0, okay, because Y2 is 0, and therefore Y1 will be equal to just this height from the 250 meters from 200. So that means that's going to be 50 meters. That's our vertical height Y1. And then velocity 1. What did we say velocity 1 was? Well, remember that this area is quite large compared to area 2 or area 3. So velocity 1 is approximately 0. So that means this term goes to 0. And, we don't know velocity 2. So we do know velocity 3, but we're going to need to find velocity 2 before we can solve for this. Pressure 2 is what we're looking for. So we know pressure 1, we know this term here because we know the y1 is 50, but we need to find that velocity 2. And where's that going to come from? Hopefully you'll recall that we can use the continuity equation, because the intake volume flow rate here at 2 is the same as the outtake volume flow rate at number 3. That's based on the continuity equation. Remember, the same amount of mass per unit time that flows through 2 is the same amount of mass that flows through number 3. So let's write where area 2 times velocity 2 equals area 3 times velocity 3. Now if you remember that this is a probably in a form of a circle here, so this is really, we can replace the area with pi r squared, velocity 2, and then pi r3 squared, velocity 3. And then we have to go back to that information that we have written up above, and you'll see it says that the 100 centimeter diameter intake, and then we have over here a 50 centimeter diameter going through the nozzle at number 3. So there's number 3, and then this is the beginning at number 2. So we have a radius 2 of, well, it's 100 centimeters divided by 2 because they give you the diameter, so that's 50 centimeters. And then we have a radius number 3 of 50 centimeters divided by 2, which is 25 centimeters. Well, regardless, actually, you could just say that radius 2 is twice radius 3 at the exit nozzle at number 3. And so you could replace that into here. You have pi 2 r r3 squared velocity 2 equals pi r3 squared velocity 3. You'll get a 4 pi r3 squared velocity 2 equals pi r3 squared velocity 3. And we'll see a bunch of things that cancel out, like pi and r radius 3 cancels out. And you get velocity 2 is actually 1/4 of velocity 3, or 1/4 of 70 meters per second, which is 17.5 meters per second. Okay, so now what we're ready to do is to plug in everything. We've got our y1 now, we have our velocity 2 now, we have everything else, and we're looking for pressure 2. And we'll assume that pressure 1 is an atmospheric pressure. So pressure 1, so I'm going down here now and continuing this. We have 1.013 times 10 to the power of 5 pascals. That's pressure 1, plus the density of the fluid, which is 1,000 kilogram per meter cubed, times g, which is 9.8 meters per second squared, times y1, which is 50 meters, and plus, well, that term is 0. And then pressure 2 is what we're looking for, plus 0, that's assumed to be 0 because it's the lowest height, plus 1/2 times 1,000 kilograms per meter cubed, times velocity 2 that we just figured out, which was 17.5 meters per second. And so go ahead and put that in your calculator to find out what you get for pressure 2. And you'll get a pressure of 438,175 pascals, and that's clearly not the answer that we have down below. That's because that's the absolute pressure at 2. And what the question is asking you above is what is the difference between the inlet pressure, which is what we found, and the pressure at that depth without the fluid moving. So what we're looking for is the difference between this moving pressure, I suppose at 2 when the fluid's moving, versus if this wasn't moved. Say if this was closed, what would be that pressure at that point, when as if this was a static fluid. So finding what the hydrostatic pressure is at 2. So let's compare that. Let's find that pressure. Really, let's go back to what we were saying that we cannot do. And if this were closed, what would pressure 2 read? And then take the difference between those two values. So pressure 2, if it was static, would be pressure 1, which is the atmospheric pressure, plus rho g h. That's 1.013 times 10 to the power 5, plus the same term that we have here, 1,000 times 9.8 times 50. So what we'll get is 591,300 pascals. And so what we're looking for in B is actually the difference between those two pressures. And so that would be this pressure, we'll call that pressure if it's static, versus the pressure when it is actually moving, the hydrostatic pressure versus what the actual inlet pressure is. So that would be 541,300 pascals minus 438,175 pascals. And that gives you a pressure of 153,125 pascals, which can be converted to about 1.5 atmospheres. So that's the difference between the intake pressure, which is right here, versus what the hydrostatic pressure would be if the fluid was not moving. Okay, and that's it for example number 9.